Hey everyone. All right, so we're starting our new unit. And this unit, we are going to be talking about waves. So, up until this point in physics, we've basically used what we would call a point mass model when we're talking about how stuff moves. And a point mass model, just like in essence, is like I have a box, but I can pretend it's all at one point right in the center and that it all moves kind of in the same way. Now, this is something where when you get to more advanced physics, we don't do that anymore, right? We actually look at the box as a bunch of points and a bunch of mass, and that each of them moves a little differently. And that's one of the ways that we really refine our understanding of physics and motion. Um, but there are some things that just don't seem to move that way. And so scientists noticed pretty early on that we were going to need another way of thinking about those pieces of matter. And we're going to start this conversation with water, because water is probably the most intuitive thing that you can think of that acts like a wave. And so, yes, water is made up of a bunch of little particles. But if we were thinking about water moving as a whole body as one piece, that doesn't really seem like how water works. Instead, we think of these waves, right? Physical waves of water, um, and how those waves move and flow, and yes, along with them bring some particles, is something that's really useful for us to understand as physicists. Um, After all, water is not the only thing that acts like a wave. So, water is one. Another thing is sound. All right. And so, sound is actually made up of the little particles of air, and whether they are very compressed or very decompressed determines how we hear them. And so you'll notice that both of these drawings I just did have some similarities. There are places where it's higher or more intensely packed, places where it's lower or less intensely packed. And if we think about the motion of the wave, we could see it like alternating between those highs and lows. And there's a what we would call periodic nature to it, that there's a repetition. And in fact, in my physics class, we cover this right after we cover circular motion for a reason. And that reason is that they're both things that repeat. And when we start looking at some of the vocabulary, we're going to see there's a lot of similarities. Another thing that acts sometimes as a wave is light. And I'm going to put an asterisk here because light is not very well behaved. And in fact, if you want to think about like all the different ways we can think of light, you should go see my history of light video. We walk through all the ways we've ever thought of light and why it's kind of a conundrum. And so we are going to learn a little bit about waves, how they work, how we can do some basic calculations around them, and what are some of the big behaviors that we see. Now, I'm going to say here, I have two different kinds of waves drawn here. I have one where we're going up and down, right? Up and down, up and down. And we call that a transverse wave. And then I have a wave where it's not about going up and down, it's about kind of a side to side motion, right? So a more compressed, less compressed. And we have a couple of words for those. We may call them longitudinal waves. We may call them compressive waves. And they're honestly pretty hard for us as humans to like look at something like that and really tell where the like bigger compression is and the lower compression is. So I will say in this video and in my class, I kind of teach all waves as I draw all waves as transverse waves, just because I think it's a little bit more intuitive for us as people. But do keep in mind that depending on the wave, those highs and lows might actually be higher compression or lower compression. This is also something we get with seismic waves. So that's like earthquakes can actually be modeled as a wave, and it is also a more compressive wave. All right, so let's look at a wave. And like I said, I'm going to use a transverse wave. And you'll notice that a lot of times in science, we use a sine wave. So literally what the graph of sine of x looks like, um, in order to show a wave. It's just a really nice, like, repeating function. It's easy to do math with, and we'll do some math with it a little bit later. All right, so some things that you need to be able to label. Let's look at our y-axis, actually. Amplitude is 1. And so amplitude is the height of the wave from what we call the center line or midline. And amplitude generally tells us about the intensity of the wave. So if it's a sound, it's how loud it is. If it's a light, it's how bright it is. We go to amplitude for intensity. There are some other parts of this wave that are interesting to us. So we see these places where the wave is contacting the midline or center line. We call those nodes. And then these highs and lows, we would call, what's the opposite of a node? It's an antinode. But, and we'll see this a little bit later in this video, it's sometimes important for us to distinguish between a high and a low specifically. So you might also hear the highs called peaks or crests, or the lows called troughs. And then the last thing that we're going to want to be able to know in terms of like the anatomy of a wave is the measurement of one repeat, right? So how long it is from when we start a wave to when we end. When I say how long, there's actually kind of two measurements that we might be interested in here. And those two measurements are as follows. We're going to use a lambda. It's a Greek letter. Think of a capital X without the top right corner. And that is the wavelength. It's measured in meters or centimeters or nanometers. It's a distance. And it's literally how long is a wave. But then we also, if I say how long is a wave, I might also think about the period. And this is something we talk about in my circular motion unit as well. And the period is literally how many seconds it takes to do one go through of the wave. And wherever we have period, we will also have frequency, which is how many waves per second. So period is seconds per wave. Frequency is waves per second, which has a specific name. It's called hertz. And so do remember that those are inversely related. So one of the most simple calculations we can do with a wave is about its velocity. And if we think about it, velocity is distance over time. So that velocity would just be how long in meters a wave is divided by how long in seconds it takes to go by. So wavelength over period, or because of that inverse relationship between period and frequency, wavelength times frequency. So for example, if I know that a sound wave travels at 343 meters per second, this is the actual speed of sound, and has a frequency of 343 hertz, what is its wavelength, I can go to velocity equals wavelength times frequency, 343 equals lambda times 343, and we'll get a wavelength of 1 meter. Now, I talked a little bit about how the amplitude determines the intensity. The wavelength determines some other quality of the wave. And in the case of light, it determines color. And in the case of sound, it determines pitch. Is it a high note or a low note? Now, what's interesting is that both sound and light pretty much always move at the same speed, at least as long as they're in air. And the speed of sound is, as I said, 343 meters per second. And the speed of light, which actually has a special name, it's lowercase c, it's a really common physical constant, is 3 times 10 to the 8th meters per second. This is particularly interesting because this speed of light seems to be a universal speed limit. We've never been able to make something go faster than that. And in fact, we have a hard time getting anything pretty close to that. What that means when these things have a pretty constant velocity is that generally speaking, when the wavelength goes up, the frequency goes down. And vice versa. When the wavelength goes down, the frequency goes up. You can actually see this pretty well on something that we call the electromagnetic spectrum. So if we look at this, let me switch my sharing. All right. So if we look at an electromagnetic spectrum, it's basically a way of organizing light by wavelength and frequency. So you'll see that the wavelengths here are really, really long and get short. And then down here, that means that the frequency is low and goes up. And so we've got radio, microwave, infrared, visible light, ultraviolet, X-ray, gamma ray. So if you know the wavelength of your light, you can tell what type of light you're dealing with. And I think it kind of freaks some people out to think of all of those things as light. But it turns out light is really just waves of electrical and magnetic fields that are around us. And all of those things are also waves of electrical and magnetic fields. And so it is completely correct to call all of those things light. Light travels at 3 times 10 to the 8th meters per second, regardless of which of those kinds of things it is. I'll point out the things on the right of that are low energy. So things like radio waves, things that are around us all the time and we don't really worry about. Things on the left are very high energy, things like X-rays or gamma rays, which if you ever have radiation done for like cancer, you're usually using gamma rays and they intend to destroy cells. And one of the reasons they can do that is they are very high energy. People talk a lot about radiation, but radiation comes in lots of different forms. And I think it's really important to understand that before anybody gets too worried about any one specific form. Some forms of radiation are absolutely very worrisome and can cause damage, and some are not. And so do keep that in mind if you ever hear somebody use the term radiation. First of all, we don't always mean like nuclear radiation, and in this case, we're not talking about that. But even when we're not talking about nuclear radiation, high and low energy still becomes a really big deal. radiation really is just a way of moving through air. And I think that's what a lot of people miss, is that radiation happens to heat. It happens to lots of things that are very, very safe. All right, so let's get back to waves then. We've talked about the parts of them. We've talked about doing some simple math around their velocities. We've talked about categorizing them through amplitude and wavelength and a tool like the electromagnetic spectrum. Um, let's talk about some of the most important behaviors that waves show. And these behaviors are honestly part of the reason we have waves in the first place. One of the reasons that we needed to come up with like an explanation for these behaviors, because our previous point mass model just doesn't explain these behaviors. All right. So the first one is something we're going to call diffraction. Which is the bending and spreading of a wave. Now, if we think about particles or point masses, they move in straight lines. In fact, that's like one of Newton's laws of motion, right? Is that like a thing's going to keep moving in the same direction unless I apply an external force to make it do something else. And so if you have an obstacle and you've got a bunch of point masses moving around it, some of them are going to bounce off. Some of them are going to keep moving through, but you're going to end up with a pretty substantial dead zone here of where there weren't particles moving in that direction, or the ones that were moving in that direction all got blocked. Now, this is not what we see with waves, and it's one of the things that makes waves really special. What we would see in this case with a wave, and so think about, like, for example, a water wave and a rock. So the wave hits the rock, and yeah, it breaks up to start with. But as we get further and further from the rock, it starts to come back together. And so, yes, you do still have a dead zone, but it's a much smaller dead zone, and it closes itself really quickly. This is a behavior that is specific to waves. You also see this, like, for instance, when you play a sound in a speaker. And if I play that sound, if it were particles or point masses, then they would just move straight out in a straight line. And somebody here who's not quite in that straight line wouldn't be able to hear. But that's not what happens. Instead, when we have a speaker playing sound, it spreads out to fill the space. And as a result, somebody standing over here, not quite in line with the speaker, still gets to hear some music. So this is diffraction. And it is one of those things where if you see some type of matter demonstrate diffraction, then you automatically know a wave model is probably the right way to think about that. The next one is interference. And interference has to do with what happens when two waves are in the same place at the same time. And it could be 2, it could be 3, it could be 8. And we basically can categorize this into 3 types of interference: constructive, destructive, and what I'm going to call other. Constructive interference is when two waves are essentially what we call in phase. Their peaks are at the same place and their troughs are at the same place. And what does that end up creating? It ends up creating a taller wave. Makes it louder if we're wanting to use sound as an um, example. Destructive interference is what happens when the opposite is true, when we have highs and lows paired together. And what happens there is they cancel each other out. We don't end up with any sound. Now, being perfectly in phase and perfectly out of phase are two very, very like examples that are not very common, right? Like we usually see things that are not either of those. And when that happens, we can get all sorts of shapes. All right. So let's take a look at this because honestly, the best way to understand interference is actually mathematically. So if we take a look at a graph, and I'm going to use Desmos, which is like my favorite online graphing calculator. All right. All right. So we're going to set up two waves. I'm going to call them f of x and g of x. So they are going to be, for now, perfectly in sync. Okay, so my red wave and my blue wave are exactly on top of each other. And then I'm going to set up my interference, which is really just adding those two waves together. And so what do I get when I add two waves that are identical and have an amplitude of 1 together? Well, I get a wave with the exact same wavelength. You'll notice it takes the exact same time to go through one cycle, but double the amplitude. And in fact, constructive interference doesn't necessarily have to be two identical waves. What if one of these waves is larger than the other? Right? Well, what ends up happening is I get an even larger wave. All right. Now let's say they're two identical but opposite waves. So every peak has its valley, every valley has its peak. What happens when we add those together is we get 0. So if we wanted to use sound as our analogy, and by the way, I have a two-source interference pattern where we go through this with sound. It's one that you can really hear what happens. Then we end up with a complete quiet spot if this happens. This is actually, for the record, how we end up with noise-canceling headphones. Noise-canceling headphones are playing the inverse of the sound they hear around you, and it helps cancel out that sound. All right, last thing is, what if they're not perfectly in or out of sync? So I'm gonna have these two. Okay, so I've got two waves. You can tell there are going to be places where they're both high at the same time, and that's going to build up some kind of wave. But there's also going to be places where they're both low at the same time, and probably some places where they're opposite or working against each other. So like here at 4, I've got a pretty high high and a pretty low low. All right, what do I end up getting? This monstrosity. And so it really is any kind of shape is possible with enough sounds getting canceled out, built up, interfering with each other. Um, these are really interesting. So we've talked about how constructive interference sounds really really loud, and destructive interference sounds quiet. But we can also look at some of those others. And one of my favorite ways to think about this is actually tuning a violin. So when you're tuning a violin, the oboist in your orchestra or your tuner will play concert A, which is 40 hertz. Uh, and you're trying to get your A string to sound like concert A. But of course, usually it's a little off. Maybe it's a little flat. Now, the way that you can actually tell that when you're listening is something called beats. So let's listen to both. You may hear that vibration sound, that it's not me. I'm playing two solid tones. That is interference. And by the way, if this isn't coming through my speaker super well, like go try it out for yourself. It's super, super cool. But actually, as you get further or closer from that note that you're looking for, the rapidity of that beat of those beats, which is what we call this again, beats, will change. Right now I'm a little flat, and it's pretty rapid. But if I get closer, now it's and I can get closer. And when I hit the note, it goes away completely. So this is that other type of interference. And I just think it's super cool. Another place that you see the other interference is if you look at the ground, like a parking lot where there's an oil spill when it has rained. And you'll see like those rainbowy kind of effects. That is actually light interfering with itself and creating weird waves that are different than the other waves that are around. So that's another really great example. All right. Thank you for joining me as we talked our way through waves and their anatomy and why we use them, and talked a little bit about diffraction and interference. Next up, we're going to look at how diffraction and interference work together to create something called a two-source interference pattern. Thank you so much. Bye.